Antwerp. So I will speak about some, let's say, ongoing project, which is a bit of side project, but I think I wanted to speak about it today because it's how I got to talk to Arne 2 years ago, I guess. So, sent him an email. So that's the reason I'm here, essentially. And so I will speak about relative V categories. And so, since I know that somehow it's a bit of a heterogeneous background, I guess I will try to make the talk completely self-contained. So I hope that I will succeed. So what are relative V categories? So first, what is a V category? It's like a category, but you have home objects instead of home sets, which are taken in some monoidal category V, which is the base of enrichment. So for instance, you could have, instead of having a set of maps between three objects, maybe you have an abelian group structure on the set of maps, or you have a topology on the set of maps, or whatever. And of course, you have then a composition law using the monoidal structure. That should satisfy some associativity and unitality conditions that you can imagine. So, what are relative V categories now? So, first, what is a relative category for V equal to set? So, a relative category is just the following very simple structure: is a category C together with a class of arrows W, and we just ask that W contains all isomorphisms. Actually, it's not even necessary. You could also ask that it contains all identities, yes, and that is closed by composition. So essentially, it's just a subcategory that contains all the objects. And you want to think of these as some kind of special maps that you want to remember. So what is it that usually you want to do when you have such a pair of things? Sometimes what people are interested in doing is inverting them, making them isomorphic. And you can always do this, modulo some self-theoretic issues. So you can always build another category CW-1 such that whenever you have a functor f that sends every mod W and W to an isomorphism, there is a unique extension like this. And here every map, every V is an isomorphism. So, for example, the derived category of a ring is obtained this way by inverting the quasi-isomorphism. Okay. So, what is a relative V category now? It's just an enriched category, which is such that the underlying category that you can always define is a relative category. So it's very simple structure. Maybe I should say how the underlying category is defined. So it's just defined by mapping out of the unit. So the home sets in the underlying category are just the set of morphisms from the unit to this home option. Okay. So an example is if you consider a ring, you can see it as an V-enriched category with one object. V-enriched means it's enriched in abelian groups. So there is an abelian group of maps, and the composition is the product of the ring. And now, if you have some multiplicative set in the underlying, so this is just a set of maps in the underlying category of the. So this is one example of relative category. So why are relative categories being studied? So essentially, for this reason, in some sense, but also because important examples of relative categories are given by model structures. So what are model structures? They were introduced by Killen, I think in 1967. Quite a long time ago. And so what is a model structure, very briefly? So you start with the relative category. You ask that W satisfies Q out of T, which means that whenever you have some triangle this type, if two maps in this triangle are in V or in W, so is the third. And then, once you have this structure, you ask, so these are usually called the weak equivalences. In the context of model structures. Then you ask that you have two other maps that you call trivial cofibrations, another class of maps, fibrations. Then you ask for a class of map that you call cofibrations, and a class of map that you call trivial fibrations. And these must interact nicely with this structure. So what does it mean? It means that this should be two weak factorization systems. Again, what does this mean? So it's quite a simple thing. So whenever you have a square of this type, if you take a map, if this map is here, you say that this has the right lifting property against this map or against this class of maps. Whenever, for every map here, you can always lift. There is a lift that makes both these triangles commute. Similarly for this, and you ask that tick off. This is exactly the class of maps having the left lifting property against fib. Same thing for fib. against kickoff, and the same axiom should hold for this. And moreover, you ask that whenever you have a map, a general map in the model category, you can always factorize the map with some arrow that is in kickoff and some arrow that is in field, or with some arrow that is in cop and some arrow that is in field. Both. You have both these factorizations. Moreover, on top of this, you have to ask that this is well behaved with respect to, all the structure is well behaved with respect to this with equivalences, which means that you have to ask that Tkoff is equal to Koff intersected W, and that the fib, the vibrations, is equal to the fib. The trivial vibrations are just given by the vibrations intersected with each. This is usually the most difficult part to prove, to show that some model structure exists. So it's a bunch of axioms. Usually model structures have this habit that they exist. There are many examples, but it's usually quite difficult to prove that they exist. So why are model structures interesting? At least to me. Or why have they been studied so much? So you can do many things with model structures. So in some sense, they are a way to understand homotopy theory. Is a presentation for homotopy. So you want to study the homotopy theory of certain mathematical objects, and you can do so by finding this model structure, putting this model structure on some category. So for example, a trivial example, so if C is any category W isomorphism, then you can take all maps, so Tkoff all maps, Tkoff isomorphism, vibration all maps, vibration all maps, trivial vibration isomorphism. This is a model structure, it's the trivial model structure. And another example is to take simplicial sets, which are functors from delta O to set, and you can put a model structure here with what you call weak homotopy equivalences, simplicial weak homotopy equivalences. And vibration satisfying certain lifting properties against horns. Which are certain shapes, like for n equal 2, there are shapes like this. And this is a model for the homotopy theory of spaces. So in some sense, this is the topologist way, or the algebraic topologist way, I think, of modeling spaces. When some algebraic topologists say space, usually they mean this. They mean a simplicial set, a fibrant simplicial set in this model structure. So what can you do with a model structure? You can define mapping spaces. So if you have two objects, x, y, in M, so, and there is this choice of weak equivalences in M. So I said before that you can formally invert the arrows. So you get some offset like this between x and y. But in a model structure, so this is a set, in the localization where you formally invert all the weak equivalences of M. But if you have a model structure, you can build up a space between x and y by taking resolutions. So in some sense, you substitute x with a certain co-simplicial object in M, which is well behaved. Then you replace y also with some replacement. But the point is that these classes of maps, the fibrations and the cofibrations, they allow you to, and the factorization properties, they allow you to resolve objects. So substitute objects by a more well-behaved one. And in fact, here I'm resolving the objects by substituting with a co-simplicial object in M that in degree 0 is weak equivalent to x. And here I'm replacing y with some well-behaved objects that is weak equivalent to y. And now I get a space because here I can, these are co-simplicial objects, so it gets a simplicial set, which is a counter. And now the point is that you can compute these things with these structures by understanding the structure of cofibrations and fibrations and so on. And the P0 of this thing is precisely this. It's precisely what you do in the localization when you just invert the arrows and make them isomorphism. But now I have more information because I have all the higher homotopy groups. So the idea, the basic idea that I would like to convey is just that with model structures you can do some enhanced version of localization where on P0 you get the usual localization, but you have a higher multiplications. And So this structure is not, these mapping spaces, they do not give you, so remark, you do not get a strict enrichment in simplicial set with this. So it's not an example of a V category in the sense that I said before, because you don't have a real composition. And so there is this question is that was addressed, I guess, in the 80s, is can you strictify to get a real enrichment in simplicial set? So can you really make it a simplicial category? And the other question is, how much does it depend, or actually, does this depend on the cofibrations and vibrations? So, or rather, how much of this structure is, in some sense, just a tool to compute this mapping space, and how much is, in some sense, how much these mapping spaces depend on this structure? And this was addressed by Dwyer and Kahn in a series of papers in the 80s, where they proved that so given a model category M, you can always strictify and find a simplicial category, which is a real simplicial category, such that these mapping spaces are such that whose mapping simplicial set are weakly homotopy equivalent to the ones in the model structure. And moreover, they show that you can build this just out of the weak equivalence, using just the weak equivalence. So in other words, these mapping spaces do not depend on the cofibrations and fibrations. They do not depend on the model structures. They just depend on the weak equivalences. And then the model structure is like a basis for a vector space that allows you to do computations. But these mapping spaces that do not have this strict enrichment, actually they have some kind of homotopy coherent enrichment. So they give you an enrichment up to homotopy in some sense. So they are really anything. So this really says that there is an infinity category associated to M, which is given precisely by this kind of weak enrichment in spaces. And the point of Dwyer-Kahn work was to say these kind of weak enrichment in spaces can always be strictified to a real enrichment. It only depends on the weak enrichment. And nowadays, what you do to get an infinity category out of M is a weird process in some sense, because then you first strictify, And then you take the multiplicatively nerve and you get a quasi-category. So first you have something which is already in some sense a multiplicatively enrichment, but to make sense of it in some sense, first you strictify the solution enriched category, and then there is a process to build a quasi-category, which is a model for infinity categories, which is very well behaved. Okay. So another thing that model structures allow you to do is to compute the multiple limits. And so I will just tell you, I will not tell you what limit is. I will not give you a definition, but I will just tell you why would you want to have a multiple limits in the first place? Why aren't the limits already good? So there is the basic problem that you want to solve with the multiple limits is that sometimes you have diagrams like this. Maybe you have two disks, and you have a circle, and you have a push out, and here you can put a point, and these are weak equivalent. And here you can put again the circle. Here you can put the trivial map. So these are weak equivalences. And so if you take the colimit here, you get a sphere, and here instead you get a point. So this is not, of course, weak homotopy equivalence. So the point is that colimits do not preserve weak homotopy equivalences. And so this is why we need to use homotopy colimits, because we want to glue in a way that is invariant by weak equivalence. This is something you could want to do whenever you have some C and some W, and you want to glue objects, and since these are some special maps that you are interested in, you want this gluing to preserve these maps. And model structures give you a way to compute these homotopy colimits using these cofibrations and fibrations. And so let me arrive to the enriched, to what I want to really talk about is that somehow you have two. So the question is, so the question that in some sense got me into thinking about this stuff is how much of this can be carried over to the enriched context. And if you see colimits, you see homotopy colimits as some generalization of of colimits, and you also have the enriched, so this is some sense the homotopical generalization. This is some sense an enriched generalization where you pass from colimits to enriched colimits. Enriched colimits are just some version of colimits that are convenient for enriched category theory. In some sense, in what way you can somehow mix these two in a way that you retrieve ordinary colimits by restricting either the base of enrichment for V equal to set, or you restrict the weak equivalences to just isomorphism. So if you have some enriched homotopy colimit, you would like that overset, and in some place where weak equivalence are just isomorphism, this is just a colimit. And the other question that one can ask is, how can you see a relative category as an enriched infinity category? And somehow the thing that I want to stress is that when you have a model structure, or when you have a relative category, here you have this is just a plain category. So the weak equivalences allow you to pass from an enrichment in sets, from a strict enrichment in sets to an enrichment in spaces. That you don't assume beforehand. Just having these weak equivalences give you somehow these enrichment in spaces without assuming it. So I would like somehow something like this also to happen in the enriched context. Because in some sense, there is another way in which you can see a V category, which I don't know if I will have time to talk about, but if on V you have a model structure, so you remember the model structure that you have on V, you fix it, then in some sense every V category C becomes an enriched infinity category. But you are fixing the model structure, you are choosing it. So I would like to know if instead I can see a relative V category as an enriched infinity category, and there is some model structure that is in some sense canonical, that you don't have to make choices. And then of course one should study how these two notions, which in principle are completely fine, they should interact. Okay, so how do you make sense, first of all, how do you make sense of model structures in the enriched context? Enriched model structures. And these were, there are two actually, there are two versions of enriched model structures which have been defined. Now I will follow the one that was given by Riedel. And this retrieves all model structures over B equal to set. The other one you cannot does it. Okay, so what is an enriched model structure? So I told you what is a model structure. So let me just say what is the basic difference, I guess. The basic difference is that instead of having ordinary lifting properties, which vibrations and trivial cofibrations and trivial vibration and cofibration must satisfy. So in an enriched model structure, you have enriched lifting properties that I just denote this way. You say that G has the left lifting property against F, if and only if. So I'm assuming that the model structure is tensored by the base of enrichment. If and only if B tensor F has the ordinary lifting property against G for every B in B. So this is the essential difference between ordinary model structures and enriched model structure, that you need to account for the tensors by every object. And so now if I want to mimic what happens in the ordinary case, where I get this enrichment, this big enrichment in spaces, now I need to find some model structure that plays that role, that plays the role of the model category of spaces. So I need to put a model structure on simplicial objects in B. That will be an analog of the Kiel model structure on simplicial sets. And there is, in some sense, there is only one choice that works, which is the following. So if you have a simplicial object in V, for every n, you can look up a set, which is the set of maps from V to Xn. It's a set. So in particular, varying the n, this becomes a simplicial set. And now whenever you have a map of simplicial objects, you get a map of simplicial sets. And you ask that this is, so you can define, a model structure can be specified by saying what are the trivial vibrations and what are the vibrations, because everything else is determined by the lifting properties. So now I just say that this is a vibration, whereas trivial vibration in given for every V in V. So this gives me an enriched model structure in the sense of real. This model structure is not trivial to, it's not trivial to prove that this exists. It exists, for instance, over some nice additive category, it exists over extensive category. It has been proven by various people, Hobby, Christensen, Gambino, Henry, Sattler, Zunil. There are many people who have worked on proving the existence of this kind of model structures. And the nice thing about this model structure is that it satisfies, so this proposition, so this satisfies a universal property, which makes it really like the model structure for spaces. So the homotopy theory of spaces has a universal property. It's the free co-completion by homotopy co-limits of a point. So you start with a point and you saturate by homotopy co-limits and you get all spaces. This is the universal property, and you would like something like this to happen with this model structure if it's the one that really mimics. So the statement is that whenever you have a V factor, gamma, whatever V factor, and C is any V category whatsoever, and N is an enriched model structure in the sense of real, so here you have a kind of unit embedding. Here I consider V functors from C to this. This is what I denote simplicial objects in V. And whatever diagram you have, there always exists an extension where F is a V functor, a left Killen V functor. Left Killen means it's a version of left adjoint for homotopical functors. So it's a left, and it is unique in the homotopical sense. So when I say unique, I mean it means an contracted. So now, of course, here I could also put a relative V category. I would just have to put some, I would have to do some boost localization here to impose these numeric equivalences. So boost localization is like imposing a shift condition. So now what does it mean, this statement?
Can I have a question? So, what you're now doing in the enriched setting is you start with the V-enriched category C, right?
Yeah.
And then the first thing you're trying to do is build that simplicial category that you built that was built before for the non-enriched.
Now I will talk about that.
Okay.
But first I want to build, where do the mapping spaces should be, right?
In which, as we want to create the mapping space, it should tell you like simplicial.
Exactly.
And then you want there to have a model structure to speak about space or count.
Exactly, and this is the one.
Okay.
And why this is the correct one in some sense, it's because it satisfies this universal.
Okay.
That is the same universal property of, this is just says that.
So is it known that enriched functors into an enriched model structure inherit a structure?
So now how do I define the mapping spaces? I use this. I take C to be a point, or the free category on a point, so that a V functor into M is just an object. Here I have this Y0 that goes into SV. Now I have a homotopically unique right-killer V functor. And this is precisely the mapping space out of M. And why does this give an enriched infinity category? So what do I mean by enriched infinity category? Because it's not so clear. So enriched infinity categories, contrary to ordinary categories, are quite difficult to define, to make precise. Exactly as infinity categories, because you have this weak composition that is only unique apart contractible space of choices. You have associativity, which is just a path. Then you have higher coherences between paths and higher coherences between higher coherences between, and so on to infinity. So there are various ways to make sense of this. And there is a theorem. What, in some sense, for some definitions of enriched infinity category is a theorem of Gertner-Hausen, but you could also take it as a principle in some sense. Or if you want principle, that an enriched infinity category, any definition of enriched infinity category that you might come up with should satisfy the following: that if you have a V module, so you should say that a V module is an enriched infinity category. And V modules are much easier to define because it's just, so C is a V module when you have a monoidal functor from V to the endomorphism of C. Here I should have said a closing. And you say that, so this is an infinity category V. Maybe let's call it K. So many V's. Okay, C is some infinity category C. And you say that C is a K module when you have a monoidal functor. This is a monoidal infinity category. It's very, because it's just composition of endofunctors. This is the most easy way to show that something is a monoidal infinity category. You want to see it as some infinity category of endofunctors. And you say that this is closed when fixing C, the inducing functor from K to C has a right adjoint. And then you define the mapping space to be C to A. And with a little work from this theorem, you can show that somehow the underlying infinity category of M, so let's say just M, is an SV module. And so, in some sense, every model structure, in the sense of real, gives rise to and the mapping spaces are precisely computable by this right adjoint. And they live here. So now maybe I should give example of what does this multiple theory looks like in some, I think that nice example, if you take V to be G sets, so sets equipped with some action of a group, then this model structure, which should be the G equivalent multiple completion of a point, is some model structure on G equivalence initial sets. And if you just look up the definitions, this is precisely what multiple theories have been calling for a long time, the genuine multiple theory of this space. So now let me just finish. So I said that there was another definition of somehow a rigid infinity category, which is the one where you fix a model structure on V. And so there is a corresponding notion of a rigid homotopy limit. So maybe one should try to understand the relationship between the two. So now you have this diagram. This is some sort of unit embedding that I already wrote down before. Now you can take another unit embedding here to just functors from C to D. And here V, you choose a model structure. And this should be well behaved, because you cannot do this thing with general models. It should be a good one. Then if it is a good model structure, what you can do, you have some enriched model category M, and you can ask whether M is well behaved with respect to this model structure. This is the usual definition of the classical definition of a enriched model structure. It says that you have a model structure here that is well behaved with respect to the model structure in V that you have fixed and chosen. So, and when this happens, there is a very nice thing that says that in some sense, if you do the ordinary, so let's say that here you have some functor. Let's say that here you have some functor f. The ordinary weighted colimit or tensor product becomes a left-Killian functor because M and V interact so well. But at the same time, if V is well behaved, it is also a V model structure in the sense of real, which means that we also have this. and this depends on mu. So you have something like this. And now you have a diagram like this, which is the composition, but since this is homotopically unique, these are actually equivalent. Which means essentially that if you can compute this by this, because you have this computation. So they actually do interact well. And if you now suppose that what's very well behaved model structure, the trivial one. Let's fix on more the trivial. And let's take V equal to 7. Then this, a model structure which is well behaved with respect to the trivial model structure on set. What is that? Is just a co-complete category with V to be isomorphism. It is false. If you ask that is a V model structure and you have set, then the weak equivalence must be isomorphism. So then this becomes actually an isomorphism, and it says essentially that when V is set and when W are isomorphism, your multiplicatively limit of F is just this, which is just a point. If mu is iso, tensored by F, which is just a collimator. And so you do retrieve everything with this definition. And it's 1 hour, so I finish it.